Happy Tuesday, everyone. I hope you've all had a great weekend. The problem I'd like to do today accompanies what was covered in problem number 24. We'll take the result of what we did there and apply that in this situation. In the end, we're going to compare just how different the results are between projectile motion in an idealized setting with no fluid resistance versus when we turn fluid resistance on. Let's start with the easy projectile motion stuff in part A first. If I'm throwing a rock upwards, which we'll call the plus y direction, recall that at the top of the throw, the y velocity of the rock becomes 0 before it starts to come back down. If we know the initial and final velocity in that situation, along with the acceleration due to gravity, well, the projectile motion equation that we could use is this one. Let's make a slight adjustment to it, though. If I'm calling the upwards direction positive, we should probably switch out this acceleration variable with minus g, like this. The quantity that represents how high the rock will rise is this delta y variable, so let's isolate that one. I'll move the initial velocity squared term over to the left-hand side first, and then divide both sides by minus 2g. When we plug in our numbers, the negatives in the numerator and the denominator will cancel out, and we end up with a positive 1.84 meters, and that's 1/2 of part A complete. To get the time it takes to cover that distance, we'll grab another projectile motion that you've seen many, many times. This one. Like before, I'm going to replace the acceleration variable with minus g, and now I want to solve for the time. Remember, the final velocity is 0 at the top of the throw, so let's plug that in straight away. Then we can swing this minus gt term over to the other side, divide both sides by g, and that's it. Plugging in the numbers tells us that the rock covers that distance in about 0.612 seconds. That's all of part A done. Time for part B. If you've watched problem number 24, this process will look pretty familiar to you, except this time we're going to make a change in the coordinate system. I'm going to leave the upward direction as plus y. This approach results in a positive distance in the end, and that looks a lot better than trying to interpret a negative distance with things upside down. There's only two forces acting on our rock, the weight and the fluid resistance pointing in opposite directions. Don't forget to include an acceleration vector off to the side. And that's it for the free body diagram. The sum of forces analysis is also pretty basic. In the x direction, nothing is happening, so that's just 0. In the y direction, our sum looks like this. If you are using the same axes convention that I am, with plus y facing up, be sure to include a negative for ma on the right-hand side there. Other than that, there's no more simplification required here, but we do need to grab an expression for what the terminal velocity looks like. And thankfully, that's really simple. Recall that once an object hits terminal velocity, there's no more acceleration. So that's what we're seeing here on the right-hand side. I've replaced the v velocity variable with v sub t to represent the terminal velocity, similar to what we saw in video number 24. And we're going to isolate that variable by exchanging the weight with mg, moving that over to the right-hand side, and then dividing both sides by k. And that's it. We're going to use this to complete part B. In part A, we started solving for the height first, and then we did the time second. But for part B, we're going to start with solving for the time first instead, since we're going to need that in order to get the height. Our sum of forces expression is up here at the top, with the normal variable v back in its spot. The first thing I'll do is exchange the weight with mg, followed by switching out the acceleration with its definition, dv over dt prime. If you are unsure why I'm using dt prime here instead of a regular dt, I would recommend taking a look at video number 24, where we covered the reasoning behind that. The next step is to divide both sides by k, and then replace this mg over k chunk, with our terminal velocity variable, which will look like that. We can also eliminate this negative sign on the right-hand side by multiplying both sides by -1, and that will switch the order of the variables on the left-hand side, as you see here. Let's additionally divide both sides by the m over k ratio here to place it on the left. Don't forget to invert it. At this point, we're free to use our separation of variables technique, which involves multiplying both sides by dt prime and dividing both sides by the velocity difference in the parentheses. Both sides are now considered separated. The next step is to integrate. On the left-hand side, we're going to integrate from the beginning time that we're throwing the rock, t is equal to 0, to the time it takes to reach the maximum height, which I'm calling t, hence why we're using t prime. On the right-hand side, we're doing things a bit differently than we saw in problem 24. We are integrating from our initial velocity, v sub 0, or v naught, whatever you'd like to call it, to the instantaneous 0 velocity found at the top of the throw. The left-hand side is easier to deal with, so let's start there. The integrand for this integral is just 1, and when you integrate 1 with respect to t prime, you're going to get t prime as a result. Evaluated at these endpoints here, well, the left-hand side just turns into k over m times t. There's nothing super complicated about that. On the right-hand side, our approach is still pretty familiar. We saw that in problem number 24, when we took the integral of 1 divided by this velocity difference, we ended up with this negative natural logarithm result. And it's still the same here. It's just that the endpoints are a little bit different. And when we apply those, our expression will simplify to this. Remember from the last video that the difference of a logarithm can be written as a single logarithm. And the notation is a little inverted here because of the endpoints that we used, but if you're adding a negative number to a positive one, well, that's the same thing as subtracting it from a positive one. So it's almost like in this line here, we have the natural logarithm of this difference minus this natural logarithm. And that falls into the same form that we need to have a single logarithm, like this. Okay? The positive one ends up in the numerator, and the one that we're subtracting in the denominator. And all the stuff inside this natural logarithm is known. We have values for that. We're free to plug in the numbers. When we do that, okay, be sure to use a -2 for the terminal velocity, by the way, since it's a velocity that represents how it's falling downward. All the units here will cancel out, and we're taking the natural logarithm of a pure number. In fact, it's just 4. Remember that we want to get an expression for t, so let's divide out this ratio on both sides to put m over k on the right. But now the question is, well, what is m over k? Here's a helpful reminder. Earlier, we said that mg over k is the expression for our terminal velocity, which we were told is 2 meters per second, but it's negative because of our coordinate system setup. Well, if mg over k is just minus 2, well, I can divide both sides of this by g. And now I know what that ratio is. Don't forget, we did say that g is negative 9.8 meters per second squared in this coordinate system. So this is what we're going to plug in for our time equation in the red circle. When we do that, the units for meters will cancel out. 1 instance of the seconds units will cancel out. And 1 divided by 1 over seconds is just seconds. The negatives here will cancel out as well, and we're left with a positive time, like it needs to be, with the proper units. And that's 1/2 of part B done. Now that we have the time it takes to get to the max height with fluid resistance turned on, we can figure out how much distance is traveled by the rock during that time period. To do that, I'm going to grab the velocity equation that we derived from video number 24. You might wonder, do we need to change anything in this equation since our coordinate system is different now? Thankfully, no, that's not necessary. The idea is to take this velocity expression and integrate both sides with respect to time. To start, we'll rewrite this velocity portion on the left with its definition. Okay? Position y divided by time, or rather position, the derivative of position with respect to time. Forgive me. I'm using a regular dt here because our integration limits won't contain t as a variable. So we're safe. We can use normal dt here. I'll still do the separation of variables technique, which involves multiplying both sides by dt. And to make sure that we don't lose any terms along the way, I'm going to distribute this dt to each term in the parentheses and then integrate each piece individually, like this. If we include the endpoints, we see that the dy term on the left-hand side is integrated from our initial position to the final, and then everything else gets integrated from the initial time of t is equal to 0 to the time it takes to hit that maximum height, the 0.283 seconds that we got earlier. One thing I would recommend on the right-hand side to start is factoring out all the constants, which are the terminal velocity term, or terms, since there's 2 of them here, and then the initial velocity term. If we do that, here's what our expression would look like. Like before, the left-hand side is easiest to do here, so let's conquer that part first. We're still integrating 1, and our integration variable is y. So if you integrate dy and you get y and you evaluate at those endpoints, well, we're going to end up with y final minus y initial. Okay, pretty simple. On the right, our first integral term is another situation just like that. Here we're integrating 1 with respect to t, which gives us t evaluated at these endpoints, like that. But instead of evaluating and simplifying, let's leave it in this form for now. At the end, once we do all the integrals, we can scoop everything up and then evaluate all of that together at the endpoints like what we're doing here. It saves us on a little bit of writing. But the question now is, how am I supposed to integrate these remaining 2 expressions here? Notice the integrands are actually the same, so it's really like we have one thing to do here. Since this requires a technique that we haven't seen in the playlist before, let's put everything aside for now and focus entirely on solving this particular integral. Once we get the result, we'll plug this back into what we were doing. To figure this one out, we need to do a process called U substitution. And for those of you who are unfamiliar with that, take a close look at the integrand here. Notice we have a function, minus km over t, buried within another function, e to the x, or rather e to the t in this situation. The outermost function is that exponential, and the innermost is this minus km times t. To do a u substitution, we're going to grab this innermost function here and set that to a new variable, u, hence the name u substitution. You can use whatever letter you like, but that's just the standard. So here I've taken u equal to our innermost function, and then I've also, on the right side, taken a derivative of both sides of this left equation with respect to time. And this is pretty easy to do because on this part, minus k over m is like a constant with respect to time. And so we're really just taking a derivative of t with respect to t, which is just 1. So that's why there's nothing over here on this side. And next, I'm going to bring this right-hand side below and multiply both sides by dt. And then also divide both sides by minus k over m. Why are we doing this? Well, this is going to be something like a conversion factor between u and t when we rewrite our integral in terms of u. I'll show that next below. So if we start with our original integral, we said that the innermost function is equal to u. So let's replace that, right? We essentially have e to the u. And similarly, we said that dt, that chunk, is equal to this negative ratio multiplied by du. So let's insert that as well. This below here, that's the u form of our integral. One thing we can do to make it look a little bit nicer is to factor this negative ratio out, because it doesn't involve u in any way. So this is what we were trying to get to, right? We want to integrate e to the u with respect to u. We just had to make sure that we kept track of this extra piece on the outside. Now, this is actually a super simple integral. If you integrate e to the u, you get e to the u. Okay, you get the exact thing out that you put in, along with that factored ratio out front. So this is actually the answer in terms of u. But an important reminder here. We have to put things back in the form of t. We only did this u substitution stuff in order to complete this integral. So if we put all this work aside to make things clear, our result to that integral is this here, what I've underlined in red. Okay, here was our factored out ratio that was negative. And then e to the u, well, you just replace u with all the stuff that we set it to. And that's actually what we need to finish part B. Let's go ahead and plug this result back in. As a reminder, this is what our expression looked like before we do that. Okay, so we had integral e to the minus k over m times t dt. When we plug this result in, pay attention to the fact that the negative ratio in our answer from the previous slide, well, that's going to invert these signs here. Okay, so this negative will become positive, and this one will become negative, like this. Now, you're free to evaluate the endpoints individually and do all that work if you like. But earlier I mentioned scooping all this stuff up and doing the endpoints all in one expression. Here's how we can do that. Notice in the second and third terms here, we have this m over k ratio along with the exponential piece. Okay, right there and right there. We can factor those out from the second and third terms and write a smaller expression that looks like the following. And then we can take the endpoints of this whole thing here in the square brackets, like this. So let's go ahead and do that. That's pretty much the last part. Recall that we had y final minus y initial on the left-hand side, which is a variable that we've worked with already. Okay, that's the delta y that we solved for in part A. Okay, so the quantities are the same. Our first expression with the endpoint of 0.283 seconds is going to be everything in these square brackets here. Just to recap, our terminal velocity and the acceleration due to gravity are negative in this coordinate system. So be sure to include negative signs everywhere you see them. Otherwise, you won't get the right answer. When we do the second endpoint, we lose the first term here because we're taking terminal velocity times 0. Okay, so that part is gone. And we also have an exponential term raised to the power of 0. And anything raised to the power of 0 is 1. So that's why that portion disappears down here. So if we take this whole square bracket minus everything in this square bracket, what do we get? Well, a positive quantity, just like we wanted, 0.659 meters. So let's bring these results together on the solution card so that we can see the differences between these two situations. So in part A, when we were using regular projectile motion equations, the rock achieved a pretty decent height in a lengthy period of time. But in part B, when we turned fluid resistance on, we're seeing a dramatic change in the results. Okay? The max height achieved by that rock, it's smaller by almost a factor of 3. And the time it takes to reach that height, well, that's smaller than the one from part A by about a factor of 2. So as you can see, there's some pretty stark differences between these two situations. And hopefully this illustrates why we need to consider fluid resistance when calculating things in the real world. That's it. Both parts are done. Farewell for now, folks. Thanks for watching.